Example 6.7.1 is sitting in our section on the central limit theorem for means. The central limit theorem is one of the most important theorems in statistics. For our class, we use it to determine probabilities of samples. Instead of just individuals, which we've done up until now, we've always been focused on individuals. What is the probability a single person has this, or a single randomly selected item? Now we're going to look at a sample as a collection. And this is important because the sample size will change our original standard deviation to something much smaller. One feature of taking a sample instead of a single item is that the sample is less variable than the single. So if I'm taking a collection of things from a big group, that collection as a whole, I find the average. That average is more likely to be closer to the true average than if I take a randomly selected thing from the same population and compare its value to the mean. Let's take a look at the central limit theorem in practice. We have an unknown distribution with a mean of 90 and a standard deviation of 15. Sample sizes of 25 are drawn randomly from the population. So let's write down a little bit of information. We have a mean of 90 and a standard deviation of 15, and we're drawing 25 on our sample. Part A, we want to find the probability the sample mean is between 85 and 92. Since we're looking at a sample mean, we want to know what's the probability that sample mean, is between 85 and 92. So the sample mean indicates that we're going to change the standard deviation. So the standard deviation we're using is not going to be 15. It's going to be the new standard deviation of the sample means will be the old standard deviation divided by the square root of n. And so this is a formula in your book. When you're given a sample, the new sample standard deviation is the old standard deviation divided by square root n. And we can calculate this. 15 divided by 5 is going to give us 3. And we can use that here in our calculation of the betweens. But we can also draw a picture. Let's draw a picture first. We've got 90 for our mean. 92 is somewhere above it. 85 is somewhere below it. We're looking at this area here. So the picture doesn't really change when we're talking about a sample mean. We have to remember to change the standard deviation. So this will still be norm.dist. It's the same function we were using before. We'll put in the higher value, 92, standard, the mean. Standard deviation now isn't 15, but 3. And input true. We're doing between, so it's a minus. Norm.dist, 85, 90, 3 again, our new standard deviation, and true. And we can calculate that in Excel, just like we did before with our other normal distributions. The big thing to remember with the central limit theorem is when we're using it, when we use the central limit theorem, we're taking samples and we're looking at the average of the samples as far as making comparisons. So we'll put in the 92 calculation. Now we're putting in the 85 calculation. We get 0.6997. And we'll write that in right there. Something I do want to note, 2 things. 1, Excel is a really powerful calculator. Meaning that if we didn't want to enter the 3, like have to calculate that new standard deviation, let's say n isn't something nice like 25 and it's 18 or 7 or 31. We don't have a perfect square root of those numbers, so we can make Excel calculate it. Right there where we're supposed to put the standard deviation, we can type in square root. Oh, sorry. Got to put in our original standard deviation first, 15, divide by square root, and then put in n. And then we can say true. And I'm going to do it again for the other one. 85, 90 for the mean. The mean does not change, only the standard deviation. Old standard deviation divided by square root of n. And if I typed it in right, we should get exactly the same answer, and we do. So you can make Excel do the calculation. You do not have to do it in your calculator and then type it into Excel. Let Excel calculate it. It's perfectly acceptable. Make some room for part B. Part B wants us to find the value that is 2 standard deviations above the expected value, 90, of the sample mean. So recalling that expected value is another name for mean. 90 is our expected value, and we want 2 standard deviations above that expected value. 2 standard deviations above the mean. This is something we can find. 90 plus 2 times that new standard deviation. And one thing I failed to mention, this new standard deviation calculation has a name. It's not just new standard deviation. We call this the standard error. We call this the standard error of the mean. So when we have a sample, we use the standard error in place of the original standard deviation. So to do part B, 2 standard deviations above the expected value, 90. We'll take that standard error, we'll multiply it by 2 and add it to 90. We're looking specifically for the sample distribution, so that's why we want that standard error for the sample distribution. And we already calculated the standard error for this problem. It's 3. So 90 plus 2 times 3 gives us 96. 96 is 2 standard deviations above 90.